Before I became the CEO of Synergetic, I was actually a lumberjack for a year. No, that was like when I was 20 years old. But I am the CEO and one of the co-founders of Synergetic Carbon Neutral Fuels. This is not a presentation about nuclear power, but it is a presentation about what we might do with it in a future that is more abundant. We are in the business of generating net zero and increasingly net negative hydrocarbons synthetically by using industrial heat and seawater. Sounds like science fiction. I did want to make a comment of science fiction before we start. A lot of the stuff that I'm going to speak on today does sound like a bright, shining future. For our version 1, and tech that will continue to iterate, all of the technology that we're going to use exists right now. There's no new science in this presentation. There's no new technology in this presentation. Maybe a few new integrations, and we will continue to iterate as we go. But when I get into the spooky stuff, trust, we've come a long way. I want to start by asking everyone to imagine what happens if our wildest dreams come true at this conference. 2030, maybe it's 2040, when we actually see the proliferation of SMRs, large reactors, and we get this abundance of nuclear power in the world. I have a lot of conversations with people in the nuclear industry, and it's fair that we've been a bit bedraggled by tough bureaucracy, tough financing. So it's a moment to start this day today. Close your eyes, think about what kind of abundance comes from actual proliferation, because we are seeing a lot of progress. This nuclear world has gone from fringe to mainstream. I mean, you guys saw COP28, tripling of nuclear. Activists turned leaders, and governments, industry, everyone's coming around to the reality that we're going to need a lot more energy, and nuclear is the backbone of those future energy demands. The bureaucracy remains, but suspend your disbelief around the bureaucracy for the purposes of this. We can come back to that in another presentation, because novel electricity demand is one thing that's really interesting. We're going to see a lot of that from a diversity of sectors. I think there's a really interesting whole knock-on effect of industrial heat demand. Industrial heat today, in its diversity of applications, is probably 99% fossil fuel fired. We need solutions to that, and there aren't many, and nuclear is easily the best one. I'm preaching to the choir on that. But in the far future, electric vehicles, sure. Data centers, we get that. What about geoengineering, terraforming, space travel, beyond interplanetary? What about intergalactic? These are things that the nuclear future underpins. And even Winston Churchill, in, I believe it was the early 1950s, he was learning about nuclear and its genesis then, and he has this quote: "Schemes of cosmic magnitude would become feasible. Geography and climate would obey our orders." I'm a big Churchill guy. I always really like that. And so emissions-free electricity underpins an era of abundance that would be hard for us to comprehend. Emissions-free industrial heat underpins a further abundance that it's really hard for us to wrap our heads around. And you guys are the ones that are making this future a reality. So thank you so much for the work you've been doing, the last 15 years, in some cases, the last 30 years. The future of nuclear power is an exciting prospect thanks to the hard work that's gone on substantially in this room. How large is our appetite for industrial heat? 99% fossil-oriented today. Since 1800, this has come exclusively from oil, coal, and gas. And I would venture that it would be difficult to go 30 seconds in your life without interacting with one of the amenities, comforts, and benefits that come from this abundance of industrial heat. We don't hear a lot about it. I read a lot of headlines around electricity policy and EVs, and let's make solar and wind turn every electrical outlet green. Fantastic. That only solves about half the problem. The rest of our energy, arguably about $7 trillion a year in global expenditure, is from industrial heat. Why don't we talk about this more? It's probably because humans are biased towards things that we see every day. Most of us have never walked past a steel manufacturing facility in our daily lives, a cement plant. But these are verticals that it will be challenged for electricity or green electricity alone to solve. So this is a problem that needs solving. It's going to get solved at some point, and I am of the view that we should just solve it today. I think current demand trends might suggest that fossil reserves will sort of become economic on about a 250-year time horizon. That's not very long in the scope of the entire existence of the human species. So let's get it right, let's figure it out. What are the best ways to solve for industrial heat? I bet you know the answer. Electricity alone cannot economically power. I'm gonna say all this stuff out loud and be the annoying guy that reads it, because think about this stuff. Mining and refining, cement production, steel production, chemical production, heavy industrial manufacturing, aviation. I flew here yesterday from Vancouver, Canada on a jet. It was a miracle. I went to sleep at 6 in the morning. I woke up, I was in an entire different country. That isn't feasible without, in this case, fossil hydrocarbons, and in the future, net zero hydrocarbons. Marine transport. So many of the clothes on our backs, the goods in our hands, the things that we're dealing with, this computer, likely that, no, not the water, came here on a fossil hydrocarbon powered marine transport vessel and hydrogen production. So what's the solve? You guessed it. Abundant nuclear implies abundant industrial heat. Even in some of the conversations we were having last night, we got bogged down in electricity. Well, we could just do more solar and wind, and there's so much solar and wind policy and credits and all these things. I say, for the purposes of this presentation, let's put that to the side. Nuclear, especially small modular reactors, have some really fantastic industrial heat characteristics. Supercritical temps, depends on who you talk to. I actually heard a core temp quoted at 700 Celsius. Also, I'm speaking in Celsius today. Damn Canadians, right? The rest of the world is on that program. Very, very hot, really hot. We can directly apply that to a variety of these industrial processes. Scalable and modular, we don't need transmission of this heat. Give me a good steel plant, I'll build you an SMR right beside it. Deployable adjacent to existing infrastructure. My team and I also deal in geothermal. I'm gonna get to that, but we really like geothermal as a co-located heat source. The problem is geothermal, especially shallow, hot geothermal, is not located everywhere. So SMRs could be. Lowest cost heat physically possible. I don't know, we'll see in the next 10, 20 years of geothermal, super hot rock especially, versus SMR, but I think we're really abutting the physical limitations of cost reduction. And of course, emissions free. And I bet you were wondering when I was gonna get to this part. This is the ideal heat input for zero, net zero, and increasingly net negative fuel synthesis. Nuclear powered fuel synthesis, the path to net zero hydrocarbon abundance. Yes, I believe in a future of increasing hydrocarbon abundance. Hydrocarbons have underpinned every technological change, advance, quality of life aspect that we have in our society. We've just been making them out of the wrong stuff. Very simple. Don't refine down, synthesize up. Start with modern, beautiful electrolyzers that have gone through incredible step change advances over the course of just the last few years. The budding and expanding and rapidly TRL increasing carbon capture world. Scrub carbon out of the air, scrub carbon out of the ocean. That carbon is an exceptionally valuable resource. We can add it to hydrogen and make that the easiest and most transportable fuel, highest energy density that we use for these applications. And then chemical synthesis. As I say, the chemistry involved in combining these hydrogen carbon atoms in Fischer-Tropsch reactors and gasification, it's not complicated. We've been doing it for 100 years. It's getting a lot better, and there's some really interesting advances that are happening. I actually spoke to an advanced researcher from Cambridge who was just doing his postdoc work with Shell. He was operating Fischer-Tropsch reactors inside an MRI so that he could see what was going on inside the reactor. Fascinating. And we're really excited about the hydrogen economy. Trust, if I could sell hydrogen tomorrow, it'd be easier for me than adding carbon into it and moving that stuff all around. Hydrogen is very difficult to transport, and there's not a lot of end-use applications today. Plus, if we say we're gonna run every engine, motor, and turbine we've ever built off hydrogen, that's probably in the order of tens, maybe hundreds of trillions of dollars worth of retrofits. Long time plan, one day, give me a beautiful hydrogen economy, I can't wait to supply for it. Ammonia, easy way to transport hydrogen, or easier, is to add it to some nitrogen atoms, and then you can move it around without having to keep it at super cool temperatures. But today, 4.4 trillion liters a year of liquid fuels, about 99% of which is still coming from fossil. We want to replace those, 1 liter at a time. Net zero synthetic hydrocarbons. This is our first and foremost effects test. I believe that we'll demonstrate this physically within the next 12 months. Very simple. Heat resource, in our case, we're gonna go with a super hot rock geothermal resource to begin. Guys, get me some SMRs on grid, get me some SMRs with some industrial heat applications. I'm happy to use them. We got, admittedly, as you know in this room, a bit more of a bureaucratic process to get there. Heat and water through modern solid oxide electrolyzer cells. We've got quite a few companies developing and iterating these. Our friends at Bloom are doing fantastic work. These electrolysis cells can accept both electricity or heat as their inputs. They operate really hot temperatures, and the physics is so simple I could explain it to a 5-year-old. Get the H2O molecule active, hot, moving, it becomes fragile. We tip a little bit of electricity in and we crack it into hydrogen and oxygen. The value product for us is hydrogen. And from there, we could look at a today functional ammonia configuration. Ammonia is really great. Fertilizer industry is $400 billion a year. We need more ammonia. And ammonia could be a great stepping stone for us to get to hydrocarbons. The integration here is to add an air separation unit. That gives us nitrogen. We run it through this beautiful Haber-Bosch reactor. It's been around a long time. We get some cool co-products, oxygen, hydrogen peroxide. These are all saleable commodities. They're super valuable and even utilized for load balancing. So this is kind of the intermediate step, but the big kahuna, net zero fuel. If we can get our heat below 4 cents per kilowatt hour electric, because a conversion to thermal, depending on who you talk to, maybe 8 to 10 times, that then takes us through to add in carbon. In our iteration 1, the easiest thing for us to do is to buy point source carbon. There's lots of emitters today that are being regulated to scrub their emissions from their smokestacks or what have you, and a lot of them are burying this carbon in the ground. That's the thesis. Let's take the carbon out and we're gonna bury it. This is a beautiful commodity. It's incredibly important. We say, don't emit it, but we'll take it. And we can buy that. Our models work at $100 per metric ton. We can buy that point source carbon for like 30, 40 USD. In the future, as direct air capture and direct ocean capture become more commercially mature, we hope to integrate those right on site as a system. This means we're scrubbing carbon out of the atmosphere and we're making fuel out of it. At the baseline, it's net zero. That's a huge improvement on the incremental carbon emissions and various other emissions, I'll come back to that come from burning fossil fuels. But where it gets exciting is increase the amount of DAC. There's also inherent loss through the system. Eventually, we could deliver a fuel that every time you fly in an airplane operated by sustainable aviation fuel from our process, you're actively segregating carbon out of the atmosphere. Host of really awesome co-products as well as we spoke to, hydrogen peroxide, methanol, waxes, greases, all the stuff we make out of hydrocarbons, we want to make out of synthetic hydrocarbons as well. Mark my words, synthetic fuel powered by geothermal or powered by SMR lives in the not possible range. We're going to produce fuel that has a higher energy density than fossil today. I'll come back to why that is. We're going to produce fuel at a lower cost than fossil fuels with no beta risk. All of the inputs are inherently price stable. And the fast piece comes into play when we consider that over the next 30 years, oil and gas supermajors plan to spend $26 trillion only on resource replenishment. It is getting harder and harder to find new oil fields and new reserves. It becomes an economic problem, 26 trillion earmarked. So we're saying we just build one of these plants, we could operate it in perpetuity. Synthylene fuel, this is our end product. Why is it great? Drop-in substitutable. We need no retrofits, no overhauls. We can operate it in existing motor, engine, and turbine infrastructure. We are not asking any of our consumers to change their behavior. We want them to continue to act in their own economic self-interest. We just want them to buy the best grade fuel they can at the lowest price. If they don't believe in climate change, I don't mind. The reason why we're doing this is deep and intimate about solving some of our climate problems. My customers don't have to be morally aligned to that thesis. Unprecedented scalability. All we need is water and heat. As long as there's water and heat, we can expand beyond the restrictions of biofuel limitations. We can expand beyond the limitations of fossil fuel reserves. Proven component parts. We're not inventing anything new. There's no new science. There's no new technology. The hydrogen effects test I pointed to all the way through to that full syn fuel configuration, they can operate with off-the-shelf catalog items today and molecular purity. When we refine oil into kerosene, for instance, it's rife with impurities, not us. Instead of refining down, we build the molecules from the ground up, and it gives us a molecularly pure output, which you can see on this slide. This is my favorite image. This tells the whole story. We're estimating that our fuel has 7% higher energy density than fossil hydrocarbons, than fossil kerosene Jet A. That implies that planes that flew exclusively on that, it's not really how it works right now. We'd blend the SAF into existing fuel resources, but over time, planes can fly higher, planes can fly faster, planes can fly in places in the atmosphere with less friction, and as a result, they're creating second-order efficiency. As I mentioned, there's no beta risk here. We don't have to be hamstrung to the ebbs and flows of the fossil fuel input economy, nor the biofuel input economy, and those do fluctuate, unfortunately, correlated with food prices. Siting anywhere, adjacent to demand. Military airports, large airport consumers, we can put these plants adjacent to the consumption, and we don't need to take on as much transportation cost and transportation risk. Domestic energy security, Russia, the Middle East, these are nebulous places, unclear as to where the future of our reliance and relationship and friendly relationships with those will go. Imagine a barrel of kerosene Jet A that says made in America on the side. It's a compelling opportunity. The contaminants in fossil Jet A include heavy metals, aluminum, arsenic, cadmium, chromium, copper, iron, mercury, manganese, nickel, lead, zinc, as well as noxious gases like sulfur dioxide and other ground-level ozone-forming gases. We kind of get honed in on CO2. CO2 is not the only problem in the atmosphere, and so we solve for second-order issues that are beyond just that. We're going to be consuming a lot more aviation as a society. 7.5 billion people have never flown on a plane. They want to. Projections are tripling of jet fuel demand by 2050. You can see there's a little blip on the graph. That's the pandemic. Barely made a dent. Did not change our long-term consumption behavior. Solving for sustainable aviation fuel is an issue that the airline industry is critically aware of. The EU has set mandates. By 2050, they expect 70% of kerosene to be not necessarily synthetic fuel, but sustainable aviation fuel. 2030, that number is 5%. Right now, we're on track to miss those mandate targets by 40%. So we've already got a massive delta of pent-up demand. And unfortunately, the limitations of the current incumbents in the sustainable aviation fuel space, they're about 95% biofuel. They've got a real big problem, and that is that they're forever and a day about 5 times more expensive than fossil fuels. Right now, they get away with that because of subsidy, but we also just don't have enough waste food oil in the world. If we could somehow collect all of the French fry grease in China, we would still be maybe substituting 0.1 or 0.2% of liquid fuels. So this is a problem that needs a novel first principles solution, and synthetic fuel is that solution. Breakthrough unit economics, this is important. I want my customer to make a self-interested economic choice. This is the greatest mechanism to enable progress on climate consumption and climate change, is to just ask people to buy the best grade product they can at the lowest price. By using heat from a small modular reactor or from geothermal and operating these new solid oxide electrolyzer cells with greater efficiency, we can get to perhaps between 80 cents and $1.20 per kilogram hydrogen. That underpins our ability to then buy that carbon, less than $100 a metric ton, combine it for an end fuel price in the 50 to 80 cent per liter range. The 10-year historic moving average of Jet A is 80 cents. So we will definitely benefit from subsidy. Those subsidies exist for a reason. It gives us a beautiful margin ramp to be able to get to scale. But at the end of the day, subsidies can't last forever. We need to give people a better option, and this target cost range, the maroon line is the current estimate for SAF. It's not actually a commodity. It trades on more one-to-one deals, and like some airline customers are paying 700% price premiums for SAF versus Jet A. The orange line is the historic price of fossil Jet A, and then this band is our target cost range. Beyond net zero, take the carbon out of the atmosphere, make it into fuel, put it back in the atmosphere again, that's great. There's some other contributions that we make that actually increasingly make us net negative over time. First of all, the system is not perfectly efficient. So maybe it's 15 or 20% of that carbon is lost in the system. Maybe we sequester that, maybe we reintegrate it. Direct air capture, really exciting. We've seen crazy explosions in that space. I think Lower Carbon Capital made 68 investments in direct air capture last year. It's a kind of an index fund approach. Direct ocean capture, we have some really cool friends that are doing the same thing but pulling it out of the sea, and they're making great progress. I think they're living at about a TRL 6, and we're going to see that commercialized in industrial use in collaboration with a large shipping company in the next 2 years. Second order reductions come from the inherent inefficiencies in fossil fuel refinement. To turn a barrel of oil into kerosene, you need to burn an additional 45% of that oil. So the refinement process, incredibly lossy. It's a second order efficiency. And then further material reductions, the elimination of emissions intensive exploration and extraction activity. Think about going to find new oil reserves and digging them out of the ground, especially when you think of Canada. We've got tar sands up there, and it's really, really pricey to get it out. It takes a lot of energy to turn it into anything usable. We don't need to do any of that. We just need to build the infrastructure, make sure there's water coming in, heat coming in, fuel coming out. What are we doing right now? Admittedly, very early stage. We really couldn't even envision this bright future just 2-3 years ago. The solid oxide electrolyzer cell advances, the advances in geothermal, the advances in SMR, we're living at the confluence of a bunch of existing step change advances, and we're standing on the shoulders of giants. So in the next 12 months, engineering model, conceptual design report. We'd love to work with US national labs or universities. I'm sure some of you guys have some experience there, probably some war stories. Help my naivete, tell me what I'm missing, help me figure out how to navigate those politics. Effects test. The digital twins are amazing these days. We can create machine learning and AI enhanced virtual environments that give us a very deep understanding of many, many different iterations of how best to maximize efficiencies from our systems. But as we know, investors love physical things. So plugging in, very simply, a geothermal asset to a solid oxide electrolyzer cell, this has never been done. It's a novel proof. We're really excited to deliver it over the course of the next 12 months. And pilot site assessments. Geothermal is the core focus for now. Luckily, there's some really hot rocks and great places that are fun to do business in. Alaska, Texas, here we are. There's a lot of geothermal here, and built on the back of some incredible wildcatters, some really smart operators from the oil and gas industry we look forward to working with. Iceland, think about Iceland. This is a big black volcano, lots of energy there, and other friendly nations. So here it is, superior grade, higher energy density, lower cost, self-interested choice, net zero, increasingly net negative. The crew that I've been lucky to tag along with on this ride have been imagining this future their entire careers. We are at this inflection point now, and it's on the back of many different converging technological changes. This may be the most important mission of the 21st century. We've got to get off fossil hydrocarbons, but our society is deeply reliant on hydrocarbons. What are we going to do? We're not going to change the engines, the motors, and the turbines quite yet. We're just going to change the hydrocarbons. Come chat with me after. I'll buy you a beer. Let's have some laughs. Thank you so much for the work that you do. That's our show today. Do we have time for cues, or I'm done?
Starting out with geothermal, how directly do you think applying nuclear process heat to the solution you're looking for?
We would way rather use nuclear process heat. If there were a few SMRs that were idling and needed somewhere to put their energy, we would love to capitalize on that. Geothermal has a host of different risks. Pulling it out of the ground, complicated and expensive. When it's really hot, it gets more complicated and more expensive. Operating at 350, 400 degrees Celsius, maybe that's functional with the materials we've got today. To get into the 500 plus, that requires some new materials advances. Heat temps up, down, fluctuate. You can draw down on your heat reserve. As you scale it, you need many, many, many wells. Like we're talking, if we were to wanting to get to a gigawatt, that might be 1,000 wells all tied into one system. No one's ever contemplated that for geothermal before. So in short, there is no better heat input for us than an SMR, especially one that operates above 500 Celsius. Natura, Copenhagen Atomics, I want to talk to you guys.
What's the upper limit of the temperature you're looking to use?
Solid oxide electrolyzer cells increasing their hydrogen separation efficiency in terms of energy in and ultimately cost up to 700, I think 750 is probably like the absolute ideal. But the cool thing about those cells is that they could accept 120 degree wet steam and they still have efficiency, incremental efficiency gains over the historic PEM and alkaline low temperature electrolysis systems that really have been around for like 100 years. So anywhere, beggars can't be choosers. We could get 250, we'd love it. 300, even better. 400, even better. And as we move towards integration with SMR, that is when we can really tailor it to the maximum efficiencies.
What volume of seawater would you be ingesting? I'm guessing it's probably really small, but anything no regulatory agencies would be concerned about, but do you have any idea?
The amount of water will be pretty substantial. For 1 kilogram of hydrogen today, we would need about 9 kilograms of fresh water. The likely application is going to be on a either seabed or near shore mounted platform, because being close to abundant seawater is really important. We also have to get crazy good at desalination. The hydrogen production inputs needs to be essentially lab grade water. Now, luckily, there's a lot of valuable stuff in that brine as well, including a lot of thorium, as I've been led to understand. So about 9 kilos of water for every kilo of hydrogen. That hydrogen kilo as well, there'll be some inefficiency loss. So you could probably look at it as a 10 to 1 or 15 to 1 liters of water input to liters of fuel output at a rough estimate.
Very good. Well, let's thank Dan for coming all the way from Vancouver.
Thanks, John.
Thank you, man.
Appreciate it, brother.
Absolutely.